Have you ever wondered what the world would look like if you could zip past it at an incredible speed? Imagine flying in a spaceship so fast that planets and stars become streaks of light. It sounds like something straight out of science fiction, doesn't it? For over 100 years, scientists, physicists, and thinkers have pondered this very question. What would an everyday object, like a simple football or a cube, look like if it flew past your eyes at nearly the speed of light? Our everyday experience doesn't prepare us for such extremes. We see cars, trains, and aeroplanes, but they move at a snail's pace compared to the ultimate speed limit of the universe. This question isn't just a fun thought experiment. It gets to the very heart of how space, time, and light behave in the most extreme conditions imaginable. For the longest time, the answer seemed simple, at least on paper. Based on some very famous ideas, it was believed that objects would appear squashed or compressed in the direction they were moving. Think of it like someone pressing down on a soft rubber ball until it flattens into a pancake shape. This idea, known as Lorentz contraction, became a cornerstone of physics. It suggested that the faster you go, the more flattened the world would appear to be. So, a perfect sphere would look like a squashed egg, and a cube would look like a flattened box. It was a mind-bending concept, but it was what the mathematics seemed to predict, and for decades, this was the accepted picture of our high-speed universe. But what if what the math says and what our eyes would actually see are two different things? This is where the plot thickens. Seeing an object isn't just about its physical shape, it's about the light that travels from that object to our eyes, or to a camera. Light itself has a speed limit, and this fact introduces a fascinating twist. The light from the back of a moving object has a longer journey to reach you than the light from the front. This time delay, however minuscule it might seem, can drastically change the image that is formed. It means that simply looking at an equation for physical contraction might not give us the full picture of the visual reality. This leads us to a fascinating scientific quest to actually see what a near light-speed object would look like. Since we can't just build a spaceship that travels that fast, we'll get to why later, scientists have had to get incredibly clever. They needed to find a way to create this incredible visual effect right here in a laboratory on Earth. The goal was to move beyond pure theory and capture a real image, an image built not from equations on a blackboard, but from a physical experiment. This challenge called for brilliant minds and cutting-edge technology to bridge the gap between a century-old prediction and a modern-day photograph, finally answering the mystery of what we would truly see. To understand this cosmic speed puzzle, we have to go back to one of the most famous scientists in history, Albert Einstein. In 1905, he introduced his theory of special relativity, and it completely changed how we think about space and time. Before Einstein, we thought space was just space and time was just time, separate, constant, and the same for everyone. But Einstein showed us that they are woven together into a single fabric called space-time. And here's the really cool part. How you experience space-time depends on how fast you are moving. It's not absolute, it's relative. This was a revolutionary idea that turned physics on its head and set the stage for our light-speed mystery. One of the most mind-boggling consequences of special relativity is something called Lorentz contraction. This idea says that when an object moves at a very high velocity relative to an observer, its length in the direction of motion appears to be shorter. It doesn't actually get squashed like a piece of fruit, rather the very space it occupies seems to shrink from the observer's point of view. So, if a sleek, futuristic rocket were to zoom past you at 99% of the speed of light, you would measure it as being significantly shorter than the astronauts inside would. To them, everything inside their rocket would seem perfectly normal. It's a bizarre two-way street of perception. This concept of contraction led everyone to believe that if you were to take a photograph of that super-fast rocket, it would look flattened. A sphere traveling at near light speed would therefore be captured as a flattened disk. This was the logical conclusion, and it was taught in physics classrooms for decades. The universe, according to this view, would become a distorted, compressed place when viewed from the fast lane. The faster you go, the flatter things get. It seemed like a straightforward, albeit strange, consequence of Einstein's groundbreaking work. The maths was solid, and the logic appeared to be inescapable. However, this is where a crucial detail was often overlooked. The Lorentz contraction describes the physical measurement of space, but it doesn't directly describe what a photograph or our eyes would see. The act of seeing involves capturing photons, particles of light that have traveled from different parts of the object. Because light travels at a finite speed, we don't see the entire object at the exact same instant. The light from the parts of the object that are farther away takes longer to reach us. At normal speeds, this delay is completely unnoticeable, but when an object is moving close to the speed of light, this tiny time difference becomes incredibly important and creates a spectacular illusion. Just when everyone thought the case was closed on squashed space objects, a new idea emerged in the late 1950s. Physicists James Terrell and Roger Penrose independently realized that everyone had been missing a piece of the puzzle. They pointed out that while the Lorentz contraction is real, it doesn't account for the visual effect caused by the time it takes light to travel from the object to the observer. They argued that you wouldn't actually see a flattened object. Instead, you would see something completely different and in many ways, even stranger. This effect became known as the Terrell-Penrose effect, or Terrell rotation. Here's how this optical illusion works. Imagine a cube speeding past you from left to right. As it gets closer, the light from its front face reaches you, but because the cube is moving so incredibly fast, by the time the light from its side face, the one that was originally hidden from view, reaches you, the cube has moved forward. This means you end up seeing both the front face and the side face at the same time. The visual information from the back of the object catches up, so to speak. Your brain and a camera would interpret this information as if the object has been rotated, allowing you to see its side. So, instead of a sphere looking like a flattened pancake, the Terrell-Penrose effect predicts it would still look like a perfect sphere. It wouldn't appear squashed at all. The distortion would manifest in a different way. The surface details on the sphere would appear to warp and slide around as if it were turning. A cube, instead of looking like a squashed rectangular box, would appear rotated, revealing one of its trailing faces that should have been invisible. It's a powerful illusion where the object's geometry seems preserved, but its orientation in space appears dramatically altered. It's a bit like a cosmic magic trick performed by the laws of physics. This theory presented a fascinating contradiction. An object can be physically measured as contracted, while simultaneously being visually perceived as rotated. Both Einstein's contraction and the Terrell-Penrose rotation are correct. They just describe different things. One describes the physical state in a specific frame of reference, while the other describes the resulting visual image. For decades, this remained a purely theoretical prediction. No one could actually test it because we simply can't accelerate a physical object like a cube or a sphere to such incredible speeds. The energy required to do so is astronomically large, making the experiment impossible to perform in the real world. The illusion remained confined to the pages of textbooks. Since we can't send a camera flying past an object at nearly the speed of light, scientists had to flip the problem on its head. What if, instead of a fast-moving object and a stationary camera, they used a fast-moving camera and a stationary object? This is precisely the brilliant approach a team of physicists recently took. They couldn't build a real camera that fast, but they could simulate one using an incredibly clever setup involving laser light and highly specialized equipment. They set out to capture the first ever experimental image of the Terrell-Penrose effect, turning a decades-old thought experiment into a visible reality. The experiment was ingenious. The scientists used what is known as an ultra-fast, gated camera. You can think of this camera as having the fastest shutter in the world, one that can open and close in just a few picoseconds. That's a few trillionths of a second. They then fired extremely short pulses of laser light at an object, such as a small cube. This laser pulse acted like the object moving at light speed. As the pulse of light swept across the stationary cube, it scattered off the surface. The ultra-fast camera was positioned to capture this scattered light, but it only took a picture of a very thin slice of the event at a time. By firing the laser pulse repeatedly and slightly changing the camera's timing for each shot, the team could capture a series of these incredibly brief moments. Each image was like a single, frozen slice of time and space, showing how the light scattered from one tiny cross-section of the cube. They then took all these individual slices, hundreds of them, and stitched them together using a computer. The process is similar to how a CT scanner in a hospital takes multiple X-ray slices of a person's body and combines them to create a full three-dimensional image. In this case, the scientists were building a single two-dimensional image from many moments in time. The final result was breathtaking. When the scientists assembled all the slices into a final image, It showed a cube that looked exactly as Terrell and Penrose had predicted. It appeared rotated, not squashed. They repeated the experiment with a sphere, and once again, the image showed a perfectly circular sphere, just as the theory of the optical illusion suggested. These were the first ever experimental photographs of this relativistic effect. It was a stunning confirmation of a theory that had, until now, existed only in mathematical equations and computer simulations. The experiment beautifully demonstrated that even the most abstract predictions of physics can be tested and proven with human ingenuity.